Let's take a look at constant and linear functions. So these are polynomial functions or functions given by polynomial expressions which are of degree 0 or degree 1. So f of x, the function, is of the form, can be written in the form mx plus b, okay, where m and b are constants and x is clearly your variable. And just to reiterate what I've just said, the degree determines if you're constant or if you're linear. So degree 0, so this is constant, so that would correspond to m being 0, or degree 1, that's linear. These are polynomial functions. So, what I want to do is just go through the basic properties of these, introduce some hopefully familiar terminology, and just make sure we really understand these. So the key fact here is that if I take a function like this and I graph it, I get a straight line, a non-vertical straight line in the xy plane. So the graph of y is equal to mx plus b is the straight line with slope m. I'll explain that in a second. With slope m and y-intercept b. So remember what the y-intercept is, it's where it crosses the y-axis. Slope m and y-intercept b. So very important, make sure this is highlighted. So let me remind us what these mean. The only one that really requires a bit of time is, I think, the slope. So the slope is a numerical measure of the steepness of the straight line. So a numerical measure of the steepness of the straight line. In the xy plane. So let me just recall what it is. So recall. So if I give you a straight line, and let's assume I give you two positions on it. So let's mark the point here, x1, y1. Let's mark the position here, x2, y2. So these are two distinct points on the plane, not the plane, on the straight line. So they're different. That's what I mean when I say distinct. Well, then the slope is the number given by, so the slope is equal to y2 minus y1 divided by x2 minus x1. And it could be the other way around too. It could be y1 minus y2 divided by x1 minus x2. It's exactly the same because it would be minus 1 divided by minus 1, so 1, it wouldn't affect anything. So the way to think about this really is the y2, at least the way I've drawn it, the y2 minus y1 is like that length there, and the x2 minus x1 is that length there. So this is a ratio of those two sides. So it's often called rise over run. So the top is called the rise, and the bottom is called the run. This is a little bit misleading because you could be kind of going down, right? You could have a negative slope and then you're kind of dropping. So rise is a little bit of a misnomer. So this is what your m is, if you're going to compare it to the function mx plus b. And this is independent of the 2 choice points you choose. If you choose any 2 points whatsoever, because it's a straight line, those ratios are always going to be the same. And again, just to remind us, this is where you cross the x-axis, or sorry, the y-axis. So, quick example. If your graph looks like this, this is the position B. Pretty obviously, because when you feed in 0, that's what you get. So this is y equals mx plus b. We should really label the axes as always. Y, x. So I'm assuming really you have familiarity with the concept of the slope of a straight line. This is a very quick run through of it. So positive means it's kind of going up. It's like the graph would be increasing if you want. And negative, the straight line is kind of going down as you move from left to right. So it would be decreasing, as we're going to see. Just some quick examples just to make sure we're really comfortable with this. So let's do this with some graph paper. I think that's a good plan. So let's do it with some graph paper. So let's draw a few of these. Let's do it like this. So I just want to make sure we're very comfortable with this. This is such an important thing to be able to do. I want to go through kind of 3 numerical examples. And it's good to have the graph paper there, just so we can really count things out. So let's do y is equal to, let's do a half x plus 2. So it has to go to the point 2 here, that's the y, and it's got to have slope a half. So that would have to correspond to 2 along and 1 up. So the straight line would have to be this guy. Got that right. So that's the graph there. Of course, dot, dot, dot in each direction. Let's do another one, a little bit more challenging. So let's do y is equal to minus 3 over 2x plus 1. Okay, so again, that's the y-intercept. And now minus 3 over 2. So that means it's going to go down 3 and then 2 along like that. Is that correct? Yes, minus 3 divided by 2. So that means when I graph this, it would look like this. So it's going to get rid of some of this. Okay, let's do one more just for good measure. Let's do y is equal to just minus 2. So this y is equal to minus 2 is 0 times x minus 2. Okay, so you'd normally write that as just the constant minus 2. So that clearly is the horizontal line at minus 2. Okay, so this is a constant function because it has constant value, right? So the constant function, the other ones are not constant because they vary depending on what x is. Constant function, which is just f of x, is equal to minus 2 for any x. Okay, so some neat examples. Let's do some really simple properties of constant and linear functions. So let's get rid of this graph business. We don't need it anymore. So here are important properties. Of function f of x is equal to mx plus b. So I'm just going to go through my kind of core things. So first of all, I want to know what its domain is. Visibly anything. There are no possible issues. I can multiply and add any numbers I want. So the domain, let's do an interval notation, minus infinity to infinity, whole thing. And just to reiterate why this is the case, where am I? Mx plus b makes sense for any number, real number. Very nice. What about the range? Well, this is a bit more tricky. Let's go off for a moment and look at these. So the range, remember, is all the y values that get taken, and we can immediately see here that the range will kind of depend on the slope. So if you're non-negative or non-zero slope, it strikes me that every single y coordinate is going to get hit. However, if you were zero slope, only one value would be taken, which is just that position there. So we've got to kind of split this into two possibilities, rather annoyingly. So if m is not equal to 0, it's all real numbers. And if m is equal to 0, well, then it's just b itself, isn't it? Just that single value. And again, just to reiterate why that's true, if I was to kind of draw a picture y and x, and I draw, let's say, a straight line with non-zero slope, as I said, you can kind of immediately see that the range is going to be everything. Next, increasing and decreasing. So I think, again, this is pretty obvious, but I do want to remind you that the concept of being increasing or decreasing is to do with whether or not a function preserves inequalities or reverses inequalities. So you could have functions which are coming from discrete domains, so just a series of dots. So the idea of it being increasing or decreasing is more general than just having positive slope, if you want. However, it's really obvious that the slope completely determines if you're increasing or decreasing for these linear and constant functions. So in particular, if m is strictly greater than 0, this implies increasing, which means you're increasing on the entire domain. And if m is less than 0, this implies decreasing. If m is equal to 0, you're neither. Of course not, you're completely flat. So let me just show you an example, and I want to do it properly, right? I'm going to check the conditions. So let's imagine I have f of x is equal to minus 2x plus 1. I want to show that this is decreasing properly. So let's take 2 points in the domain, A and B. Let's have A less than B. So if it's decreasing, we want to show that it reverses the inequality when I feed it into the function. So let's first of all multiply by minus 2. Well, negative 2 is negative, so that means it reverses the inequality. It's one of my core properties of inequalities. So what does this mean? Well, once I've got that, I can add 1 to both sides. That doesn't change anything. So minus 2a plus 1. Adding or taking away doesn't affect the inequality, the direction. Minus 2b plus 1. And now that's exactly the statement that f of a is strictly bigger than f of b. Nice. So that says that, implies that. That's what it means to be decreasing. That's the definition of decreasing. So let me label a few things here. So this and this is properties of inequalities. And really what we have is the following. So maybe I'll just get this. So what we've concluded is a less than b implies f of a strictly bigger than f of b. That's us done. That is the meaning of decreasing. This is the definition. The definition of decreasing. Okay? Nice. It's good exercise in kind of carefully unpicking things. So it's much stronger than just drawing a picture. Right? This is a really precise statement. What else? Increasing, decreasing, bounded, I think is incredibly obvious. It's all contained in the range, really. Remember, the range is what's going to determine bounded. So maybe I'll say here, in this case, this is unbounded. So not bounded above or below. And clearly this is bounded because it's only taking one value. After this, symmetry, odd or even. So even, remember, graphically means that you are symmetric after reflection in the y-axis. That can only happen, I think, if you're a horizontal line. So let's do these guys. So the function f is even if and only if you're a horizontal line. That's if and only if m is equal to 0. And rather pleasingly, f is odd if and only if b is 0. So the y-intercept is equal to 0. So let me just show you why this is true. It's really nice. So the first one, I mean, being even, you're flat, right? So this is m is equal to 0. And it's the same after reflecting. Reflection across the y-axis. And now if b is equal to 0, what does that mean? Well, it means it's going to cross through. It's going to cross through. So this corresponds to b is equal to 0. And now this guy is the same after rotating by 180 degrees, or pi in radians if you want to say it like that, around the origin. So same after rotating by 180 degrees around the origin 0, 0. So that's what makes it odd. And if you weren't going through that, you wouldn't have that property. You need to go through the origin for that to make sense. So of course you could do this totally algebraically, right? I could check that f of minus x is equal to f of x for all x, if and only if it's slope 0. I could go through that, but I think it's just nicer to see it like this. Okay. Last property I want to look at is whether it's one-to-one. So let's do it. So this again I think is pretty obvious. If you're thinking about the horizontal line test, then it's really clear. F is one-to-one if and only if m is not equal to 0. Of course, if m is equal to 0, you're massively non-to-one-to-one because you take the value b for every single x. So just if you want a picture of this to persuade yourself, you can do it totally algebraically too. But if you want a picture, well, if I draw a straight line like this, and m is not equal to 0, so it's at kind of a slope, then if I draw any horizontal line, it crosses, well, exactly once. Because the range is all real numbers. So it only crosses at a single point, exactly one intersection. So let me just show you how you'd find inverses then in this case. So let's do it by example. Imagine I have f of x is equal to 2x minus 1. So here 2 is non-zero, so this is 1-to-1. So this tells you that the inverse exists. So remember, that's not the reciprocal, it's not 1 over f, that's my notation for the inverse function. So algebraically, to find an inverse, you kind of flip the x and the y. So we'll say x is equal to 2y minus 1, that's f of y. So now I need to solve this for y. So this is if and only if 2y is equal to x plus 1, adding 1 to both sides, and I suppose rearranging the left-hand side and the right-hand side. And now this is if and only if, dividing through by 2, y is equal to a half x plus 1. So I suppose this could be written as a half. You don't really need to do this, but I suppose it's quite nice practice. A half x plus a half. So it's another linear function, right? So this is f inverse x. And notice it's also a linear function. That's very understandable, isn't it? Because if you take the time to reflect a straight line across the straight line y is equal to 1, y is equal to x, like you do to find the graph of an inverse, it would still be a straight line. So reflecting a straight line in another line keeps it straight. So it makes sense. So yeah, just a little bit of a warning here. Some people might guess from this, just looking at it, that, oh, well, the inverse I'm just going to divide through. But that's not correct, is it, right? So maybe what they might do is the following. They might say, I'm going to divide through by 2 and I'm going to add 1. That undoes those operations. But notice that is not equal to that. So you can't second guess this. You've got to do it really carefully. It's the same kind of business as doing a succession of transformations. You can't really guess immediately what's happening. You need to do each one slowly, carefully, methodically, using the proper technique. That's what we've done here. Okay, so those are the core properties of straight lines.